There is no sound, no wind in the trees, because the trees have been erased. No bird calls, because the avian lineage will not evolve for another 100 million years. No buzzing of insects in the underbrush, because the underbrush is gone, and the insect chorus, the background static of the living planet, has been silenced. The year is approximately 252 million years ago. The place is everywhere. You are standing on the shore of a dead ocean, the Panthalassa. The water is warm, lethally warm. In the shallows, the temperature hovers near 40 degrees Celsius, hot enough to denature proteins and disable the metabolic enzymes of complex life. It smells wrong. The air carries the stench of sulfur and rot, a sharp chemical tang that burns the back of your throat. This is the scent of hydrogen sulfide, a toxic gas produced by blooms of anaerobic bacteria that have taken over the stagnant, oxygen-deprived seas. The waves lap against black rock, and nothing lives beneath them. No fish, no ammonites, no darting shadows. The great Permian reefs, massive structures built of sponge and coral that once stretched for thousands of kilometers, are white and silent. Their calcium carbonate skeletons are dissolving into the acidifying water, their architects extinct, their structures crumbling into anoxic slime. Behind you, the land rises in shades of brown and gray, folding toward a horizon that shimmers with heat haze. There is no green anywhere. The vast gymnosperm forests that covered the supercontinent of Pangaea are reduced to stumps, ash, and memory. The ferns, the seed plants, the great coal swamps of the Carboniferous, all of it is gone. The soil itself is dying. Without root systems to anchor it, the pedosphere is washing away, stripping the continents down to bedrock and choking the rivers with unchecked sediment. This is the morning after the end of the world.
The Permian-Triassic extinction event, known to science as the Great Dying, has just concluded. It is the most severe biotic crisis in Earth's history. It liquidated approximately 95% of all marine species and 70% of all land vertebrates. It devastated the insect population, a class of animals so resilient that this event remains the only mass extinction to significantly impact them. It collapsed the forests, the reefs, and the complex trophic webs that connected them. It was the closest multicellular life on Earth has ever come to total annihilation. The primary engine of this destruction was fire. Not a single forest fire, but a geological inferno erupting from a wound in the Earth's crust known as the Siberian Traps. This was a large igneous province event of apocalyptic scale. For roughly 1 million years, a mantle plume drove flood basalts across an area the size of Western Europe. But lava alone does not kill a planet. The true weapon was atmospheric chemistry. The magma burned through vast subterranean deposits of coal and carbonates, releasing carbon dioxide, methane, and sulfur compounds in quantities that defy human comprehension. The atmosphere transformed into a kill box. Carbon dioxide levels skyrocketed, trapping heat and driving global temperatures up by 10 degrees Celsius. The oceans absorbed this excess carbon, reacting to form carbonic acid, which plummeted the pH of the seawater. This acidification compromised the ability of marine calcifiers, corals, mollusks, and brachiopods to build their shells. Simultaneously, the warming ocean lost its ability to hold dissolved oxygen. Circulation currents stalled, and the deep ocean became anoxic. Then the poison rose. Euxenia, a state where water is both anoxic and sulfitic, spread from the abyss to the continental shelves, suffocating marine life and releasing toxic hydrogen sulfide into the atmosphere. To complete the catastrophe, the release of halogens eroded the ozone layer, bathing the terrestrial surface in mutagenic ultraviolet radiation.
Life did not vanish in a single instant. It unraveled in pulses over tens of thousands of years. Species that survived the initial thermal shock succumbed to the acid rain that scoured the continents. Those that withstood the acidity suffocated as atmospheric oxygen levels dropped to roughly 15%, inducing chronic hypoxia. Those that survived the suffocation starved as the primary producers at the base of the food chain collapsed. The dying fed on itself, a cascading failure of biological systems until only scattered threads of the web remained. And now, the worst is over. The volcanoes are quieting. The atmosphere is beginning to stabilize, though it remains a greenhouse prison. The oceans are still toxic, still hot, still largely empty, but the chemistry is no longer deteriorating. What remains? Bacteria, fungi, and a handful of generalist survivors clinging to riverbanks and coastal margins, disaster taxa that can endure the unendurable. In the deep ocean, where conditions were slightly less lethal, a few species of ammonoids and thin-shelled bivalves hang on. On land, walking through the ash and the silence, are the remnants, pherocephalians, small cynodonts, and the ancestors of the archosaurs. They are small, traumatized populations of creatures that happened to possess the right physiology at the right time. They do not know they are survivors. They do not know the world they remember is gone forever. They only know that food is scarce, the sun is too bright, and the herds they used to see are simply gone. The Triassic period is beginning. It will last for 50 million years. It will see the slow, agonizing recovery of the biosphere. It will eventually witness the rise of the dinosaurs, the first mammals, and the first pterosaurs. But not yet. For now, there is only the silence, the empty ocean, and the brown hills under a hazy, high-carbon sky. The Triassic begins not with a biological explosion, but with a long, slow exhale. The Earth is exhausted. The great experiment of the Paleozoic era is over, and the slate has been wiped terrifyingly clean.
Now pull back. Step away from the shoreline, away from the dead water and the ash, until the details blur into geology. Rise above the brown hills, higher still, until the scars of the extinction become planetary patterns. Rivers appear like thin veins choked with sediment. Coasts look like torn edges. Deserts spread like open wounds. From this altitude, the planet itself looks unfamiliar. From space, the Earth looks wrong. The blue marble you know, with its scattered continents, vast Atlantic and Pacific oceans, and bright white ice caps at the poles, does not exist. Instead, there is one landmass, one enormous C-shaped supercontinent stretching from pole to pole, surrounded by a single global ocean called Panthalassa. The continents have not yet begun their slow tectonic drift toward their modern positions. They are locked together, fused into a colossus that covers nearly a third of the planet's surface. This is Pangaea. The name means all lands in Greek, and for once, the nomenclature is not an exaggeration. The geometry of Pangaea determines everything about Triassic life. Consider the interior. Thousands of kilometers from the nearest ocean, cut off from moisture by mountain ranges and the sheer scale of the landmass, the heart of Pangaea is a hypercontinental desert beyond anything the modern world possesses. This is a consequence of continentality, the climatic effect of being far from the temperature-moderating influence of the sea. Temperatures here swing between lethal extremes, scorching days and freezing nights. Rainfall is a statistical anomaly measured in centimeters per decade. The sand is stained red with iron oxide, the same chemical compound that colors the surface of Mars. Nothing grows here. Nothing can. This is not the Sahara. The Sahara has oases and is bordered by moist oceans. The interior of Pangaea is a dead zone larger than modern Africa.
The coasts are different. Where Pangaea meets Panthalassa, the temperature differential between the rapidly heating land and the slower warming ocean drives a weather system of immense power, the mega-monsoon. These seasonal wind reversals bring torrential rains to narrow bands of the coastline, creating habitable corridors. Rivers flow down from the interior highlands, carrying the stripped soil of the dead continent and creating deltas where life can take hold. But the recovery of that life is hampered by a breakdown in the fundamental machinery of the biosphere. For nearly 10 million years following the extinction, no coal forms anywhere on Earth. This anomaly is known as the coal gap. Coal requires forests, vast swampy accumulation zones where plant matter piles up faster than it can decompose. The absence of coal tells us a terrifying story. The forests did not just thin out, they vanished. The biomass production of the planet crashed. In the place of forests, the geological record reveals something else, a fungal spike. Stratigraphic layers from the early Triassic are loaded with Reduviasporinides, fossilized fungal spores. This makes grim biological sense. Fungi are decomposers. In a healthy ecosystem, they are part of a balanced cycle of growth and decay. But the Great Dying broke the cycle. The plants died, the animals died, and the fungi inherited the earth. They feasted on the corpse of the Paleozoic, exploding in abundance as they consumed the rotting biomass of a devastated world. This is the silence of the early Triassic. It is not just the absence of animal calls, it is the silence of a stalled carbon cycle. The world is brown and bare, waiting for the soil to recover, waiting for the complex microbial communities to rebuild, waiting for the green to return. And in the shadows of this broken world, the survivors are beginning to move. They are the seeds of the next 200 million years, but for now, they are simply trying to endure the long, hot morning of the new world.
In the biological vacuum left by the Great Dying, the survivors are not the strongest, nor the most intelligent. They are simply the ones that can endure the longest. As the early Triassic sunlight beats down on the scorched interior of Pangaea, one creature emerges from the dust to claim the empty world. It is not a dinosaur. It is Lystrosaurus. To modernize, Lystrosaurus is grotesque. It is a dicynodont, a two-dog-toothed synapsid, making it a distant cousin of mammals, not reptiles. It possesses a barrel-shaped body, stumpy legs, and a face dominated by a beak and two downward curving tusks. It looks like a pig designed by a committee that gave up halfway through. Yet, in the immediate aftermath of the apocalypse, this unassuming creature achieves a level of dominance that no single genus has ever equaled. For a brief window in the early Triassic, Lystrosaurus accounts for up to 95% of all terrestrial vertebrate biomass. This is unprecedented. If you were to walk across Pangaea 250 million years ago, nearly every animal you met would be a Lystrosaurus. It is the ultimate disaster taxon, a species that thrives in the low-diversity, high-stress environments following a catastrophe. Its success lies in its mediocrity. It is a generalist, using its beak to shear through the tough, drought-resistant vegetation that other herbivores cannot stomach. Crucially, it is a burrower. In a world bathed in ultraviolet radiation and prone to violent temperature swings, the ability to dig is the ability to survive. Lystrosaurus inherited the Earth because it was built to live in a bunker. But disaster taxa are placeholders. As the biosphere stabilizes, complexity returns, and with complexity comes competition. The reign of the shovel lizard ends as the ecosystems rebuild, making way for a new dynasty, the archosaurs.
By the Middle Triassic, the archosaurs, the ruling reptiles, are diversifying rapidly. And deep within this lineage, a silent war is beginning. It is not fought with teeth or claws, but with biomechanics. The conflict centers on a single anatomical feature, the ankle. The archosaurs split into two distinct lineages based on how this joint functions, a divergence that will dictate the flow of life for the next 200 million years. One group develops a crurotarsal ankle. This is a complex peg and socket arrangement that allows the foot to rotate. It provides stability and power, supporting heavy armored bodies and allowing for an erect, pillar-like stance. This lineage is the pseudosuchia, the false crocodiles. The other group develops a mesotarsal ankle. This is a simple hinge joint, restricting motion to a single plane, up and down. It is less stable but far more efficient for rapid linear movement. It is built for speed. This lineage is the Ave metatarsalia, the bird-footed archosaurs. They are the ancestors of pterosaurs and dinosaurs. In the Triassic, the smart money is on the heavy ankle. The pseudosuchians explode in diversity and size, becoming the undisputed masters of the supercontinent. They are not the aquatic ambush predators we know as crocodiles today. Those are a later, specialized offshoot. The Triassic pseudosuchians are active terrestrial nightmares. Consider Postosuchus. Standing over a meter high at the hip and reaching lengths of 5 meters, it is an apex predator that walks on 2 legs or 4. It has a boxy, robust skull filled with serrated, knife-like teeth.
It looks remarkably like a distinct carnivorous dinosaur, but this is convergent evolution, nature finding the same solution to the problem of predation. Alongside it are the adiosaurs, heavily armored herbivores built like biological tanks, covered in osteoderms, bony plates that protect them from the crushing jaws of their cousins.
The dominance of this lineage is confirmed by recent discoveries. In rocks from southern Brazil, paleontologists have unearthed Tinerakiwasuchus bellator. At first glance, its gracile, agile skeleton looks like a dinosaur, but the ankle tells the truth. It is a pseudosuchian. Even the niches for small, fast hunters are being filled by the crocodile line. The dinosaurs are present, but they are marginalized. Small, bipedal runners living in the shadows, waiting for a mistake that hasn't happened yet. While the pseudosuchians conquer the land, a different invasion is happening along the coasts. The Great Dying emptied the oceans even more thoroughly than the continents, leaving vast marine niches vacant. Nature abhors a vacuum, and reptiles begin to slide back into the water. This return to the sea is a masterclass in adaptation. The nothosaurs are the transitionals. They possess elongated necks and webbed feet, capable of hunting in the surf, but still tied to the land to rest and braid, much like modern seals. The placodonts take a different approach, evolving heavy, turtle-like armor and crushing teeth to exploit the recovering shellfish populations on the seafloor. But the true rulers of the Triassic Deep are the ichthyosaurs. These creatures commit fully to the aquatic life. They sever their ties to the shore, evolving a body plan that is startlingly convergent with modern tuna and dolphins. Their limbs transform into rigid hydrofoils. Their tails develop a vertical fluke for high-speed propulsion. They evolve the largest eyes in the animal kingdom, saucers of bone and tissue over 25 centimeters wide, designed to gather the faint light of the deep ocean. Crucially, they solve the problem of reproduction by giving birth to live young, freeing them from the need to return to the beach to lay eggs.
Evolution works quickly here. Within a geological heartbeat, ichthyosaurs go from lizard-like swimmers to leviathans. In the late Triassic, they achieve sizes that defy logic. In 2024, paleontologists identified a new species from the coast of England, Ichthyotitan severnensis. Based on massive jaw fragments, this animal is estimated to have been 25 meters long. That is the size of a blue whale. The existence of Ichthyotitan changes our understanding of the recovery. It proves that by the end of the Triassic, the marine food webs have not only recovered, but have become productive enough to support predators of energetic demands and physical scale comparable to the largest animals in Earth's history. These giants patrol a global ocean that is warm, stratified, and teeming with cephalopods and fish. They are the undisputed kings of the Panthalassa. And finally, the archosaurs look up. The sky, like the ocean, is an open frontier. Insects have held the monopoly on powered flight for nearly 100 million years. In the Triassic, vertebrates finally break that monopoly. The pterosaurs appear. Their engineering solution to gravity is unique. They elongate the fourth finger of the hand to grotesque proportions, using it to stretch a membrane of skin and muscle, the patagium, from the fingertip to the ankle. This is not gliding. This is powered flapping flight. The pterosaur skeleton is a marvel of weight reduction, composed of hollow, thin-walled bones reinforced with internal struts. Their respiratory system is upgraded to power the metabolic demands of flight. The early forms, like Eudimorphodon, are small, snagging insects and fish with multi-cusp teeth. They are awkward on the ground, their wings folded clumsily against their sides, but in the air they are graceful, maneuverable, and untouched by the terrestrial predators below. By the close of the Triassic, the world is full again. The forests have regrown, the oceans are patrolled by whale-sized reptiles, the skies are filled with leather-winged hunters. The land is ruled by the heavy-footed, armored, powerful pseudosuchians.
To an observer standing in the late Triassic, the hierarchy seems set in stone. The crocodile line archosaurs are the winners of the evolutionary lottery. They are diverse, abundant, and dominant. The dinosaurs are merely a footnote, a scrappy collection of small, bipedal generalists scurrying through the undergrowth, keeping their heads down. But the Earth is not done shifting. The stability of the Pseudosuchian empire is an illusion, built on a climate that is about to break. A new weather system is forming. Clouds are gathering over the supercontinent, heavy with a moisture that has not been seen in millions of years. The ankle wars are about to be decided not by strength, but by rain. The change begins with rain, not the seasonal monsoons that sweep across the coasts of Pangaea every year, nor the scattered storms that briefly break the drought in the interior. This is something different, something that does not stop. The year is approximately 234 million years ago. The place is everywhere, and it is raining. The Carnian pluvial episode is one of the strangest climatic events in Earth's history. For roughly 2 million years, a span of time that swallows entire civilizations, entire evolutionary lineages, the planet becomes dramatically, persistently wet. The arid interior of Pangaea, the great red desert that has dominated the supercontinent for tens of millions of years, begins to shrink. Rivers swell, carving new channels through the baked earth. Ephemeral lakes become permanent inland seas. The brown gives way to green. We see it in the lithology. The sediments of the Middle Triassic are dominated by red beds, oxidized, iron-rich deposits formed in dry, oxygenated conditions. Then, abruptly, the stratigraphy changes. Dark mudstones appear, rich in organic matter. Coal seams form for the first time since the early Triassic recovery. Fossil soils, or paleosols, show evidence of waterlogging, of swamps, of conditions utterly unlike the arid wastelands that defined the epoch. Something had tipped the climatic balance from dry to wet across an entire planet.
The engine of this change was once again volcanic. The Rangelia Large Igneous Province, a massive outpouring of basaltic lava in what is now Western North America, erupted during the Carnian. The eruptions injected enormous quantities of carbon dioxide into the atmosphere, triggering a rapid greenhouse effect. Warmer air holds more water vapor. A hotter planet is a wetter planet. The hydrological cycle accelerated, spiraling into a feedback loop that turned the Triassic hothouse into a global swamp. For the creatures of the Middle Triassic, this was a catastrophe. The archosaurs that had adapted to arid conditions, the Rauisuchians hunting in dry forests, the Adasaurs grazing on drought-resistant scrub, found their world transformed. The niches they had perfected were washing away. The floral turnover was immense. Conifers and resinous trees replaced the xerophytic flora. Extinction rates spiked. The Carnian pluvial episode acted as a great filter, removing species that could not adapt to the humidity and creating openings for species that could. The openings favored the dinosaurs. This is the pivot point. Dinosaurs had been present since the Middle Triassic, but they were marginal players, small, rare, living in the shadows of the Rauisuchians. They were not dominant. They were survivors. But the rains changed the rules of engagement. The new, wetter environments favored different biomechanics and different metabolisms. The dinosaurs, for reasons we are still unraveling, were pre-adapted to this damp world. Perhaps their respiratory systems, specifically the avian-style flow-through ventilation involving air sacs, gave them a metabolic advantage in an atmosphere where oxygen levels were fluctuating. Perhaps their erect bipedal posture was more energy efficient for traversing the soft, waterlogged substrates that bogged down the sprawling or semi-erect pseudosuchians. Whatever the advantage, the fossil record is unambiguous. After the Carnian pluvial episode, dinosaur diversity explodes. They grow larger. They begin to fill niches previously occupied by their crocodile-line cousins. The rains made room for the dinosaurs.
Listen to the Carnian. Close your eyes and hear the constant patter of water on broad leaves, the rush of swollen rivers, the squelch of mud underfoot. The air is heavy, humid, carrying the scent of resin and decay. Thunder rolls across skies that are never quite clear. In the spreading forests, the calls of the new masters are beginning to sound. This is not the Triassic you imagined. This is a wet world, a green world, a world in transition. 2 million years of rain, long enough for forests to march across continents, long enough for the balance of power to shift. And then, as suddenly as it began, the rain stops. The climate swings back toward aridity. The lakes shrink, the interior desert reasserts itself, and the late Triassic begins. But the biological clock cannot be turned back. The dinosaurs are stronger now. The pseudosuchians are weaker. The trajectory is set. The first dinosaurs do not look like rulers. They are modest. Eoraptor, the dawn thief from Argentina, is barely a meter long, a generalist weighing perhaps 10 kilograms. It eats insects, small vertebrates, perhaps plants, an opportunist finding a way. Herrerasaurus is larger, a dedicated predator with serrated teeth and powerful legs, but even it is dwarfed by the remaining Rauisuchians. Yet they are spreading. The same body plan appearing in South America is found in Africa, in Europe, in North America. Pangaea is a highway, and the dinosaurs are learning to use it. By the end of the period, the first giants emerge. Platysaurus and other prosauropods begin to reach multi-ton sizes, browsing high into the canopy. They are the heralds of the sauropods to come, but they are not yet the undisputed kings. The Rauisuchians still prowl the forests, the phytosaurs still choke the rivers. The late Triassic is a Kent's stalemate. But the ground beneath their feet is restless. Deep within the earth, the mantle is churning. The forces that held Pangaea together for 100 million years are reversing. Rifts are tearing the crust apart, opening long, jagged wounds that will eventually become the Atlantic Ocean.